So let's talk about 127, because this here is probably the most important lecture of the whole semester. This is the punchline. We're going to talk about how to develop exploits, and this is where we go through the fundamental exploit, stack overflows on Linux. This is the original exploit. All the rest are based on this. They're variations on this. So let's talk about it, and then I'll have a lot of live demos. This is the heart of the whole thing. You learn how memory is used by programs, and you learn how to create exploits to handle the errors caused by inappropriate memory usage, which is pretty much entirely due to the language C. All right. A big campaign for community colleges. Oh, that's interesting. If you post a link about that, go lightly, I'll take a look. Yeah, I wouldn't try doing examples from the textbook. They're probably only going to work in old versions of Linux. I'd stick to the projects I wrote. All the books, the projects don't work. That's why it took me several years to get this class going, because I couldn't find any textbooks with instructions that work for real hands-on projects. They're all only working on older systems or something. It wasn't until I found Georgia Weidman's book in an appendix as the first buffer overflow that actually worked. And that's why I wrote my projects, and they actually work. It's just that the stuff in the books is too old. Anyway, so we'll talk about the topics here, and mostly it'll be live demos. But so here's the main thing. A stack buffer, this was a technique known to sort of the black hat and hacker world, but not published until Aleph 1 wrote it up in FRAC in 1996 and gave the first version of these instructions. And all the textbooks you're reading are going through those steps. The problem is they all seem to be for old versions of Linux that are hard to get on, and if you try to run it on a modern version, various things don't work. But that explains how this works, which was awesome. And so a buffer is an array, just a series of bytes reserved to store a whole series of numbers. So to prepare a Debian machine, what we're going to do is we're going to write 32-bit code and exploit it, even though all modern machines are 64-bit. Now in Windows, you can always run code one architecture generation behind. So 64-bit Windows can run 32-bit code natively. In Linux, they do not include those drivers, but you can add them with these instructions. Build essential GCC multilib, and GDB is the debugger. So if you install these three things, then you can run 32-bit code on 64-bit Linux, and that's what we're going to do just to make it simpler. We're going to start with the old-fashioned 32-bit code. And so let's run some exploits. Now I've got a Debian 11 machine here, and I'm running a server version, I think. But anyway, I'm just connecting with, let's go up a little bit. Yeah, and clear. All right, I've just connected with SSH. If you SSH into your Linux machine, it's not much harder in 64-bit really, and you'll see it in the projects. It's a very similar process. All right, but I'd like to SSH into my machine. This is the easiest way. Then you can cut and paste into it easily and so on. So let me make this a little smaller and over. All right, so let me do ls. All right, so I made this program ch2a.c. All right, so this is about the simplest program. It includes standard IO libraries, has one function main but no parameters, and it creates an array. Now, the way C works, when you make, I'm using VMware, but you could totally do it in a VirtualBox too. So this makes an array with 5 elements, but the way it works in C is it starts counting at 0. So this is element 0, 1, 2, 3, and 4. There is no element 5. But then I print array 5, and this is one of the many problems with C. All the problems we're going to talk about today are caused by C. C is a very efficient language because it very easily compiles down to assembly language, but it has a lot of security problems for that reason. And here's one of them. When you print an array element, it defines an array to just point to a location in memory. Then it reserves enough room to store these, and when it goes to print something, it has forgotten the previous command. It's like somebody with amnesia. When it executes this command, it just starts at the beginning of the array and moves forward to the 6th item, 0, 1, 2, 3, 5, even though you didn't reserve that space or put anything there, and just prints it out. because it has forgotten how big the array is. It doesn't keep track of that. It is the programmer's responsibility to keep track of details like that, and programmers frequently fail to. So this is attempting to print something that is off the end of this array. So when you run it, it prints this bizarre random number, which is not 1, 2, 3, 4, or 5. It's printing some memory location that's off the end. And by the way, let me point out, here's how you compile it. You GCC is the compiler, M32 means make 32-bit code, and -G means include symbols for debugging, which just makes it easier for us to see it in the debugger. Then you define the output file, which is, by tradition in Linux, just the name of the program with no extension. And here's the input file, which is the source code in C. So we're going to compile them all that way. So everything we're doing today is 32-bit code with debugging symbols. And since we have debugging signals, we can use the debugger. Now, the GNU debugger is very powerful and very hostile. You really have to get used to it. And if you go for an online tutorial, they will all be mind-boggling with 100 commands. It's very complicated, but we really only need about 6 commands. So we're only going to use the very simple features of the debugger. It's enough to do what we're doing. So GDB, I use a -Q to put it in quiet mode. Otherwise, it prints a big, ugly banner that is useless. And then the name of the thing you want to debug. The point of a debugger is you will run the program in an isolated environment, and then you can step through it step by step and examine the use of memory and variables and such. That file, ch2a, I see a question, just here, it's just right here in this directory. So I started with ch2a.c, and when I compiled it, it turned into ch2a there. And that's what I just ran here. So when you run it with /, that runs it, and it prints this array element 5, which is a strange number, not related to any of these numbers up here. How do you get these files? I just typed it in. They're pretty short. I just typed it in before class. All right. So now if I run that with GDB, and you can do it too, but just type them in. Yeah, I could put them on GitHub or something, but it's not worth it. None of these programs are more than like 8 or 10 lines long. So ch2a. All right. So now that I'm in the debugger, here's one command worth knowing, list. List will print out the code. And since I included debugging symbols, it will show me the code in C. I do not need to read assembly code. So the program is 7 lines long, and there it is. Now, when it goes to print this, I would like to know what it's doing. And let me just check my plan here. Yeah, put a break at 6, run. Okay, we'll do it that way. So line 6 is the printf statement. So I'm going to put a break there, which means it will stop before executing line 6, because I want to run the program until it's about to print something, and then I want to look at the memory and try to understand where did this weird number come from. So I run. It runs. It hits a breakpoint before line 6, and now I can examine memory. And here I'm going to examine array. So it's x/8x means show me 8 32-bit words in hexadecimal, and start them at the location where you stored that array. So I use &array to indicate a pointer to the start of the array variable. So this command here in C said, make an array with room for 5 numbers and put in 1, 2, 3, 4, 5. And here they are. Each number is 32 bits long. So here it is filling it up with 1, 2, 3, 4, 5. And when I print array 5, it's 0, 1, 2, 3, 4, 5. It prints this number. So this number, FFFF D5C0, since it starts with F, it's interpreted as a negative integer, and that's what this is, that big negative integer. And this is just some value that is stored at that location in memory for some other purpose. It's not in, and this is called an information disclosure vulnerability. I was able to see something that the program developer did not want me to see. That's information disclosure. I'm able to read something that is not inside an array of data. It's something out here that has to do with the control flow of the program, and that's one vulnerability. And you see, C did not complain, didn't give me any warnings or anything. This is the problem with C. C only looks at one command at a time, and if it can do that command, it's happy. It does not look at the context. If it was capable, smart enough to look at the command before it, it would have realized that this is incompatible with that. But it does not have any such checks. C++ is like this too. Yes, C and C++ are both like this. More advanced languages like Visual Basic and Python would not have this problem. Like this. That's the problem. C is very fundamental. Yeah, that does not mean the memory location. That's correct. That does not mean, well, the memory location has to be assigned to this application or it would just give you an error message. That would be a memory read out of bounds. So if I tried to print like array 1 million, it would give me an error because it can't even reach that location in memory. But so it's reaching memory that is being used by this application, but it's not being used to store a value that was initialized by me. And this is, you'll see a lot of this, accessing uninitialized memory is a common memory corruption vulnerability. All the stuff we're doing here is memory corruption vulnerabilities. All right, and so we can quit to get out of the debugger. It'll warn me the program is still running, but I'm going to kill it. So let me just point out, here's the commands we used in GDB. List to see the code, run to run the program, break to put in a breakpoint, and X to examine memory. Like I say, you only need to learn about 8 or 10 of these commands to do everything we're doing, and they're pretty simple. All right, so let's go to the next one, which is a denial of service. So let's look at this one, cat ch2b, oops, 2b. All right, and I'll do a clear first, let's get things kind of tidy. All right, so this one defines an integer I and the same array with 5, and now it runs a loop, and 10,000 times it tries to print the address of array element I and array element I until it's going way out, 10,000 past the beginning. So let's see what that does. If I run that, it goes, this is the address it's reading, and there's what's in there. So it reads way out here, and when it gets to FFFFDF, it's going up by 1 in this third digit from the right here. 5, 6, 7, 8, 9, A, B, C, D, E, F. So the next one would be FFFFE0 something. And before it does that, it has a segmentation fault. So this is what someone was just asking. I have read a lot of memory, and there's some point when I'm no longer in the memory. Yes, exactly. That's the end of the stack. I have hit the end of the memory allocated for this program. I'm not allowed to read beyond that because that memory is not reserved for this program. That would be some other program's memory, and the operating system protects me from that, so it prints the segmentation fault message. Very good. So that's reading past the end of an array, and that's a denial of service condition, right? It crashes. Now, let me show you, let's talk about address space layout randomization. Now, I turned it off earlier. I'm going to turn it back on. So the normal default of all modern operating systems is to have address space layout randomization turned on. And so let me turn it back on to get back to the initial state. First I have to do sudo su minus to turn into root. And now it's echo 1 to proc sys. This is just a location in the memory that controls this security feature. Randomized there. There, now it's back on. So if I now run that program I just wrote a few times, we can see what happens. So I run ch2b. Okay, this time it went a lot further before it crashed, and it crashed down here at FF95. If I run the same program again, now it's FF97. And now it's FF84. Every time you run the program, it randomly relocates to a different memory location. That's what address space layout randomization does. Every time you relaunch the program, it randomly moves it. This is a valuable security feature, but I want to turn it off for what we're doing tonight. I see, what if we added virtual alloc to this application? Could we jump beyond the stack? Yes. If you used virtual alloc, you could reserve another memory space somewhere, and then you'd be able to access that. I don't think you'd be able to force it to put that right after the end of the stack, though. but you can certainly allocate a range of memory, and then you can use it. Yes. All right. You might even be able to tell it exactly what memory you want. I'm not sure about that. You might be able to. Anyway, so that's address space layout randomization, and to get rid of it, we turn it off the same way we turned it on, which is echo 0 into this randomized VA space variable, and then leave root. Okay, and now if I run this program once and again, it does exactly the same thing. It ends at FFFDF and again FFFDF. This is running programs the way they all were about 10 or 15 years ago, back in Windows XP and earlier in Windows, and similar timeline in Linux. This is back when every program would just load in the next available memory location. And if you stop it and run it again, it'll just come back in the same location, which makes it easier to develop exploits. So anyway, now I've got address space layout randomization turned off, and that means I can now examine this in the debugger, and it will match what I see just running it here. So we saw it went to FFFFDF, and when it tried to print FFFFE0 something, it couldn't. So we put it in the debugger, Q, CH2D, and we list it. And you see here's the print statement. So let's just run it to that point to make sure it's in the right region. So I'll make this fit on the screen a little better there. So I put a break in line 7, and then I run it to line 7. Okay, now I'm just about to print these numbers, so I'm definitely in the right part of the program I want to examine. And now I look at the memory, which is info proc mappings. This shows me the memory location allocated for this program to use. And I'll make my window a little bigger and just run it again to make it cleaner. All right, info proc mappings. There you are. These are all the memory locations allocated for the use of this program. And the one we're using right now is the stack. And you see the stack goes from FFFDD to FFFE0, just like we thought. So the highest address you can go to is FFFF, 4 Fs and an E0. And as you saw up here, FFFDE, DF, this FFFE0 B8 would have been off the end. That's why it wouldn't let me do it. I exceeded the memory region allocated for this program, and that's a segmentation fault. You have exceeded the segment of memory you're allowed to use. So that's what happened. All right. So that's one more debugger command, info proc mapping, to see the memory allocations for the program. All right. So let's talk about the stack. The stack is a last in, first out object. You push things on the stack, and when you pop, you get the last one you put on. So there's an order to the objects, and it reverses the order, which is a pretty strange thing to do. If you just wanted to store normal memory things, you'd normally want random access, where you give each memory object a name, and you pick them out in any order you want. But the point of this is to handle calls to subroutines. I don't know MTG. Anyway, so here's the stack. Pop takes things off. So if you push onto the stack 3 things, and then you pop the first 2, you'll end up down here with ESP always points to the top of the stack, and the pop things off, ESP will move up. And by the way, it's low memory at the top and high memory at the bottom. When you push things on the stack, it grows into lower memory locations, which is a little screwy. Oh, Magic the Gathering has the stack. Yeah, that's true. Card games often do, where you pile things and then pull them back out. Anyway, so there's 2 pointers that control your use of the stack. The extended base pointer is the bottom of the current stack frame, which is the stack allowed for this one routine. And ESP is the top. So when you have local variables that are stored on the stack because they're only used temporarily in one module, and the memory is released when you leave that module, then you typically express them like this, EBP plus 10, from number related to EBP. That is how you point to variables on the stack, and we talked about that last time with the assembly code stuff. So the whole point of this is for functions. So when you call a function, if you're running a program and you say printf, it has to stop running your code and go run the printf code. So the calling routine stops, does not execute any commands after the printf. It saves the current state, transfers control to the function you called, like printf. That function performs its function, and when it's done, it restores the state of the calling function and picks up where you left off, the command after the printf. So this is just like you're working on something and the phone rings. You have to go talk on the phone and then come back and resume where you left off. All right, so here's what the stack looks like if you call a function. You push the parameters onto the stack, then you enter the function. The prolog saves the return value of the calling function and the EBP, which was the base of the stack frame that the calling function was using. And then it has local variables, like arrays here. The function operates, and when the function returns, it restores EBP to this value and EIP to that value, and then it can resume at the calling function. That's how it works. This is the place where it keeps track of what it was doing, so it can return to it. So that's the purpose of this. So you put the arguments on the stack, then you put the return value on the stack. All right, and so there's a prolog at the start of every function that pushes the EBP from the calling function onto the stack, and then it's ready to prepare a new stack frame by copying ESP into EBP, so it starts a new stack frame at the top of the previous stack frame, the first unused memory location, and then subtracts some from ESP to make some room to store local variables. It creates a new stack frame on the stack. The return value always stored in EAX in 32-bit code. In principle, the return value could be in any register. It is just a tradition that it's typically in EAX. And that's just the way compilers tend to do it. You could, in principle, put it in anything. But in practice, you'll normally find the return value in EAX. All right, so here's the parameters, the return value, EBP, and then local variables. And so here you are. I've got a function which defines a 5-character array or 5-integer array, and that's all it does. And a main just calls the function, and the function has 2 parameters, which, by the way, it doesn't use for anything, but it's got them just so we can watch how they're handled. So here it calls the function with the values 1 and 2, goes into the function, and when it's done, it prints that it's come back. So that is ch2c, so let's look at that one. So clear and cat ch2c. All right, so here it is. I got a function called f with 2 parameters, and all the main function does is call it and then print when it comes back. So if you run that, of course, 2c, it just prints this return from function because it didn't print anything in there. That's all it does. But if we put it in the debugger, we can see how it works. And I think I want to break at 2 points here. Yeah, 10 and 6. All right, so GDB minus Q ch2c and list. And I press enter, it'll list the rest. All right, and I want to break at 10 and 6. I think that was my plan. Yeah, which is before we enter the function and when we try to return from the function. So I break on line 10, and I break on line 6. So main will start, C programs always start at main. It's going to get ready to run the function and break. Then when I continue, it's going to go into the function, reserve the array, and get ready to come back and break again. So we're going to run it and look at the registers. So first we run it. Okay, now it is in main. It's right here. So if you look at the registers with info registers, we can see the 2 registers that are interesting to us right now are ESP and EBP. So the current stack frame for main goes from 5A0 to 5A8. In fact, let me just make a little text document up here so I can make some notes of these things. So the main routine has ESP. I'll just copy that. All right. All right, let's make that a little bigger. All right. So that's where the main routine stack frame is. Now if I continue, now I'm in the function inside there. So if I just do the same thing and look at the registers with info registers, ESP and EBP are different. And I'm going to copy them into this text document to make that easy to see. Now I'm in the function F. So the main function is up here. The stack frame goes from 5A0 to 5A8. But when you enter the function, it has to make a new stack frame using lower memory addresses from 570 to 590. And that stack frame is only used while you're in this function. When you return from that function, it will free up that memory and return to this one. So if I just continue again, it will go to here, and now it's back in the main function. And if I wanted to see that, I could put a breakpoint on the print also, which would be line 11. So let's break at 11. All right, and now run it again. All right, so here, if in the main function, I go from 5A0 to 5A8. Now if I continue and look at info registers, I'm now at 570 to 590. That's the memory in the subroutine. And if I continue more, I'm now back in the main function. And so if I look at the registers here, I'm now back to 5A0 to 5A8. So that's the stack frame being created. And let me see what else I wanted to say about this one. There we are. So we talked about that, ESP, EBP, and the other stack frame. Now let's look at the contents of the stack in that routine. Okay, so let's run it again. Start from the beginning. Here we are in the main program. I'm going to continue to get into the stack. And now I'm going to list, just to remind us of the source code, I'm now inside this F function. And the only thing in there is an array, the same array we had before with counting numbers from 1 to 5. So let's look at the stack here. If I do info registers, the stack goes from 570 to 590. So I can look at the stack with x/20x, 20 words hexadecimal, starting at ESP. So 570 is here, 590 is here. There's one of the things I mentioned last time. A confusing thing about computers is the bytes are numbered byte by byte, but they're used as words. This is 32-bit code, so it uses 4 bytes at a time. So when it tells me that the base pointer is 590, what it means is it's the 32-bit word starting at address 590, including byte 590, 591, 592, and 593. So this is the current stack frame, starting at the 32-bit word beginning at 570 and continuing to through the 32-bit word starting at 590. So that highlighted region is the stack frame of the F function. And here's those numbers. Remember the code 1, 2, 3, 4, 5 was stored in a local variable, and here it is 1, 2, 3, 4, 5. These 5 32-bit words contain those local variables, and there are some other values stored here for other purposes. But at the end of the stack frame, the next word here is the return pointer. That is the memory location it's going to return to in the calling function. And you can see that if you disassemble main, remember this is 56, 55, 61, F2. Let me make a note of that. I'm going to put it in my text document up here. The return pointer points to that address. So if I disassemble main, here it is. This is the assembly code here. So notice here it calls F. Before you call a function, you push the parameters on the stack. So it pushes 2 and 1. Those are the parameters. Then it calls F. When it's done with F, it should resume here, so that address should match this address, 56, 55, 61, F2, and it does.
Could you say that again? Sorry, I'm having trouble hearing you.
I thought I found a way to turn off that stupid voice control thing on my watch, but I guess I need to figure out how to turn it off on my phone too. How the numbers were pushed to the stack, like using 5 push. Well, that's what this command did in C. This command in C will assign those 5 numbers on the stack. And if you want to see how it was done, so this is how you do it in C. Assign 5 numbers at once. But if you want to know how it's done in assembler, we could look at the code for F. Let's disassemble F. Okay, and here you are. It's just 5 move commands. It moves it to EBP plus 4, EBP plus 8, or minus 8, I guess, minus 12, 10, and 4. That's how it did it. The compiler could also have made it into a loop or used another instruction that will copy a lot of memory. This is what the compiler does. It decides what kind of assembly code to use. Yeah. Good. These are very good questions. So there's the return pointer. Now, let me return to my slides and see what else I wanted to say about this. So you see how it calls a function. You push the arguments on the stack, and then you call the function. When you enter the function, this is the prologue. And right here you'll see it. Here's the first thing a function does is prepare the stack frame. So this function pushes EBP onto the stack, and then, which is the old EBP, and then it moves ESP to EBP, so it starts a new stack frame at the first available location that's not used, and then it subtracts something from ESP to reserve enough space for the local variables, and it reserved 20 in hexadecimal, which is 32 bytes, which was enough to store these 5 numbers and whatever extra stuff it needed to store. Yeah. Yep, that's right, you've got it. All right, so this is what's called the prologue. Every function has to begin by preparing a new stack frame and saving the old EBP so it can restore it on the way back out. And when it leaves, it goes back to the calling function. All right. So there's the saved return address. And as we saw, that matches the next word after calling F. That's number right there is the number it uses to find its way home. What function convention is that one? Is that CEDCL? I don't know. I don't know what you call it. This is the standard. I've seen it in Ghidra. They talk about different function conventions. This is one of them where you push things on the stack and the called function has to make the new stack frame. There is another one. I've seen it in Ghidra. There's another kind of function where you don't have these prologues. But this is the default for the GCC compiler. Yeah, you're probably right. I forget the terms. When we get to the Ghidra project, I'll refresh myself on those terms and we'll have it. That'll be coming up in a later lecture. But you're right, there are different calling conventions. This is the standard one used by C and GCC. All right, so now we're going to make an overflow exploit. So this is chapter CH2D. So let's take a look at that. Get out of the assembler and clear and cat CH2D. Oops, 2D. All right, so now I have a main function that calls a function called user input and then returns. And the user input defines a buffer with enough room for 30 characters, and then it calls the getS function, which is a famously dangerous function. This reads text from the keyboard of the user without any length limit. And then it just prints what it got. That's all. So if I run this one, ch2d, it's now waiting for input from me. I didn't give it a prompt or anything. It's just running getS. So I put in hello there, and it just prints back hello there. So it works fine. If your input is not longer than 30, it's fine. The window title bar. Oh yeah, thanks for telling me. Let me move that back down. Good. All right. So all right, now let's make it crash. If I run it again and give it a long input, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, I'm going to put that in a clipboard because I'm going to need it again. So that's 50 characters long, 5 A's, 5 B's, 5 C's, 5 D's, and 5 E's. And now I get a segmentation fault. So this was too big, it didn't fit, and I wrote beyond some memory limitation. So let's check my plan here. Yep. Okay, now we debug and put a breakpoint at that printf and look at it. All right, so let's debug it. If I gdb quietly ch2d. All right, now I run, and first I put in hello. Oh, it finished. I had to put a breakpoint in. All right, let's put in a list. I want to put a breakpoint here before it prints it. That's line 7. All right, now we'll run it and put in hello. And now here we are. So now, let me make this fit on the screen correctly. There. So now I can do info registers. And I can see that the ESP is 580 and the EBP is 5A8. So I can look at what's on the stack with x/20x ESP. And the stack ends at 5A8. So this is 5A0, 5A4, and this is 5A8. So that is the stack frame. This is the memory region allocated for temporary use by this routine, and this is the return pointer. And I gave it the word hello, which you can spot if you're good at ASCII. 48 is capital H, 45 is capital E. Here's the two L's, they're both 4C, and that's 4F. Now, that's kind of annoying. It's kind of hard to remember these ASCII terms. This is why you don't usually use a word like hello. By tradition, what you do is this. I'm going to run it from the start again. If you want to test something, you put in AAAA. Whoops, not Control A, but A. Shift AAAA. There. I'll put in 8 A's, I guess. There. Because they're easy to spot in hexadecimal. Capital A is 41. So if you do that, and now you examine the stack, now you can see here they are AA, AAAA, AA. There are the A's. So you can spot where they're stored in memory very easily. Exactly. Just by tradition, it's the easiest way to put a mark in that you can see in the debugger. And again, if I do info registers, I see that the end of the stack frame is here at 5A8. So that's here. So there's the stack frame, and there's the return pointer. So if I just keep adding more and more text, I'll eventually hit and overwrite the return pointer. So let's do that. I run it again. Yes. And now I put in that 50 characters I put in the clipboard earlier. And now, here's the point. I put in 50 characters where there was only room allocated for 30. And if I look at the registers, the stack frame did not get bigger. This is the fundamental problem of C. It reserves enough room for the expected size of that object, and it does not notice when I put in more objects. If this was Visual Basic or Python, if I tried to put 50 characters in something that was only had room for 30, it would automatically allocate more memory somewhere that can store 50. But C is not smart enough to do that. C will just start at the beginning of the array and write the next 50 bytes without remembering that it's not supposed to go past 30. So 580 to 5A8, if I examine the stack ends here at 5A8, and it just kept writing right past it. These 45s are capital E's. These are A, B. Here's the C. D is 44. E is 45. It just wrote a bunch of E's right over this return pointer. So now the return pointer that ought to be pointing to the calling function points to some crazy location, 45, 45. So if I continue, it will crash. And it will tell you, I tried to go to this memory location and I can't go there. Now, why did it crash? If I look at info proc mapping, I may have to run the program again to see it. There, you'll see, here's the only memory locations I'm allowed to use. Some of them start with 56, and some of them start with F7, and some of them start with FF. But those are all the memory locations this program is allowed to use, and this is not one of them, 45, 45. It's reading some memory that is out of bounds for this program, which is why it crashed. So now someone says the meaning of the number, 20 words. Yeah, 20. Yeah, 20 words, exactly. You've got x20. When I did this x20x, this means examine 20 32-bit words in hexadecimal. So that's why it showed me 5 rows with 4 words on each row. That's all. This could be any number, but 20 is convenient for these simple little programs that have small stacks. When you do the projects later, you'll have to look at stacks that are hundreds of bytes long. But these simple programs, we're using small numbers just to make it easy to see. So that is a buffer overflow exploit. That's the fundamental thing you did. We overwrote the return pointer, and therefore, in this case, we made a denial of service exploit, which causes the program to crash. But if we put a more careful value here, we could point to a valid memory location that contains executable code, and now we are choosing what code is executed, not the developer that wrote the program. This is how you take over a box. You input something that the developer intended to just be like something like text, and you trick the computer into executing code of your choice based on the text you put in, and you design it using a debugger. So we've been through that. Yep, so this is just a review. These are all the GDB commands I use to do what we're doing. This is all we're probably not going to need for the whole course. So even though GDB has 100 commands, you don't need to know them. You just need to know these. List to see the source code, run to run the program, break to insert a breakpoint, X to examine memory. You can disassemble modules to see the assembly code. You can continue to resume execution. Info registers shows you the registers like ESP and EBP. And info proc mapping shows you the memory map, showing the stack and all the other memory segments that are allocated for the use of this program. That's all you need to understand a buffer overflow exploit. So let's look at a Kahoot. I should have those Kahoots open over here. All right. So this is 127, Chapter 2. All right, my window is not the right height. There, 127, Chapter 2. There we go. Ah, Clayton's got octopuses. That's cool. I just heard on a podcast today they've added a new bunch of emojis to Unicode, and they've added a pregnant man, and some people are freaking out at that. Anyway. All right. So what language causes these buffer overflows? Good, everybody knows that. This is why the Linux kernel is seriously considering moving away from C to Rust, and so is Windows. Because for 20 years, everybody's been having memory corruption exploits in C, and it never stops. And there are other languages that wouldn't have this problem, and it might be worth switching to them. Anyway. So what memory section is the simplest to exploit? The stack is the best because you have the return pointer right there. So all you have to do is add data to one of the local variables, and if you can get off the end, you just write the return pointer, and that goes right in the EIP, so you get execution right away. What about job security? Don't move away from C. Well, that's why they've been considering moving to Rust, but they haven't moved wholesale. A lot of people still love C. C is fast and efficient, and it has the advantage that when you compile code, it gets really hard to reverse engineer. So, but I mean, a lot of people, enterprises, write all their stuff in .NET or something. Anyway, there are a lot of other languages, but a lot of people are still using C and C++ and C#, its derivatives. Yeah, embedded systems too. All right, so in this command, what is that %x in the print command? That's the format string. Like you're saying, the point of C is like a hot rod car. It is fast and efficient if you are an expert driver. But if you're a clumsy or inexperienced driver, you can easily crash. That's the problem. So if experts love C, it's almost as fast as just writing assembler, but you really have to know what you're doing. And in practice, you can't maintain code in C for a long time before somebody makes these mistakes. Well, Rust is more like an automatic transmission. Rust will do, for example, if you try to put in too much data, it will just automatically reallocate more memory with enough room. So that's like it automatically compensates for your mistakes, which is what most other languages do, which makes them slower and bigger when you compile them. You're not in as exact control of the vehicle, but safer. All right, so that's called a format string. That's the string that tells it how to print this, and %x means print it in hexadecimal. So, what register contains the address of the next instruction? That's the instruction pointer, and it's the extended instruction pointer because it's 32 bits long. So EIP. ESP is the top of the stack. EIP is the next instruction to execute. All right, where's the bottom of the stack? It's EBP, the base pointer. That's the bottom of the current stack frame. All right, so what GDB command will show you the current stack frame? Yep, that's that one. Yeah, nothing to worry about random. I know, so you put up the answer, but that's fine. That's why these Kahoots are all extra credit, These Kahoots are not like scientifically precise. They're just a way to review stuff and keep people from falling asleep. So there you are, X20 hexadecimal starting at ESP. That'll show you the first 20 words on the current stack frame, which might not be the whole thing, but for these small programs, it is the whole stack frame. All right. And what GDB command shows the source code? Yeah, list shows you the source code, and disassemble shows you the assembly code. All right. All right. That's a real name, and that's probably real initials. Maybe enough for my grader to figure out who it is. And that's enough to know. All right. let me stop this recording.